Hello viewers, so welcome back to the course on matrix computation and its application. So, in the previous lecture we have started with the basics. Now, we will continue with that one and we are going to define the another algebraic structure that is called field. So, in the previous lecture we have started with the groups and then we have shown that the set of integer is an abelian group under the operation, binary operation, that is addition, and the same way we can define that the set of rational numbers or the real numbers, they are also the group under the operation addition, or even I can show that we can show that they are also abelian group under multiplication. So, after that we going to start with the another one, that is field. So, what are the field? So, in this case suppose we have a set f. So, in this case we have a set f and we are having two type of binary operation. One binary operation I will represent by addition and another binary operation will represent by multiplication. So, that we are going to have. So, in first thing is that in the field we are going to have two binary operation and one is represented by addition and other is represented by multiplication. So, what is the field? So, suppose we have a f is a non-empty set and first thing is that f is an abelian group under the operation addition. So, it should be clear that f should be an abelian group under the operation addition, whatever the binary operation we are defining here. Then we know that under the addition it is a binary, it is a abelian group. So, we are going to have the additive identity that we represent by 0. So, in this case we just take f minus the element that is called the additive identity, that is 0. So, f minus 0 is an abelian group under the multiplication operation. So, it is also a abelian group under addition and also the abelian group under multiplication. Only thing is that I have to remove the additive identity from the set. So, f minus 0, and then the third one is that multiplication is distributive over the addition. So, there is that a star b plus c, it can be written as a dot b plus a dot c, or I can write a plus b dot c is equal to a dot c plus b dot c. So, if this is satisfied, then we say that the multiplication, so it is a left multiplication, it is a right multiplication. So, we can say that multiplication is distributive over addition. So, if these properties are satisfied, then we call that the given set f is a field under the operation plus and dot. So, that is called the field. So, let us take some examples that how we can define a field. So, let us take the set of real numbers, because this will be used in when we define the vector spaces. So, I will start with the simple one, that is the set of real numbers, or we also represent, sometime we also represent by R. So, the set of real numbers. Now, so this is my set of real numbers and I am defining addition and the multiplication. So, addition I am defining as addition, or I can take it usual addition. And multiplication I am defining as usual multiplication. Usual multiplication means whatever the multiplication we generally take for the set of real number, that multiplication we are defining here. Now, so let us start with the properties. So, let us take the first property, that R should be an abelian group under addition. So, check this one, but we can define this very fast, that okay. So, because I know that if I take x and plus y, that is also going to be a real number. So, that is also R. So, I can say that addition is well defined, and then so this is well defined. So, I can define the another properties, that associativity. So, x plus y plus z, it can be written as x plus y plus z. This is true for all x, y, z belongs to set of natural numbers or set of real numbers R. So, I can say that this is associative. Second one is that I know that 0 plus x is going to be x, and I can write this as a x plus 0, and this is true for all x belongs to the real numbers. So, I can say that my E is 0 in this case. So, this is my additive identity. Now, so after defining this one, we define the third property. So, in the third property, that for any x belongs to the real number, we can have x minus x, and that is going to be 0, and that 0 is my additive identity. So, from here I can say that because I need a plus x should be equal to E. So, in this case I can say that for any x belongs to the real number, minus x is the inverse of x. The inverse of x in R. So, it is the inverse. So, inverse means it is unique, and also I know that it is commutative. So, x plus y is equal to y plus x for all x y belongs to set of real numbers. So, this is from here I can say that under the addition it is an abelian group. So, first property is satisfied, then I define the second one. So, I have to take a set of real number minus the 0 element I am defining. So, E is my 0 here. So, it should now I consider only these things, and under the multiplication. So, I know that for any x and y belongs to R, x dot y is also a set of also a real number. So, belongs to R. So, the multiplication is well defined. So, after defining this one, I can say that this is well defined. Now, I can define that for any 3 element x, y, z, it can be written as x, y, z for all x, y, z belongs to set of real numbers, because I can say that I know that 2 into 3 into 5, it can be written as 2 into 3 into 5 like this one. So, it does not matter that whether you are calculating 2 into 3 first and then 5, or 3 into 5 then 2. So, it does not matter. So, it is associative in that case. Second one is that now I have to find out the identity element E. So, for any x belongs to, so it cannot be a 0 element. For any x belongs to this, there should be an element E belongs to this such that x E should be equal to x. So, in this case you see that this is only true because it is a real numbers. So, R, if you take 5 and 5, then E should be 1. So, from here I can say that E is 1 in this case, and this is called the identity element, or I can call it multiplicative identity. We generally represent by E dash, because that is E and it should be E dash. So, and I know that E dash is equal to 1, that is a real number. So, it belongs to the given set. So, I can say that E exists in the given set, and this is also unique. The third one is, so in the third case I need to find out the inverse. Then for any x belongs to my set, so you know that if I take any real number 1.5, then 1 over 1.5 into 1.5, that is going to give me 1. So, for any x belongs to this, I need A such that I get value 1. So, from here I know that my A can be written as 1 over x, because x is not 0. That is why we always exclude the value of 0 from here, because in this case if I take 1 over 0 infinity, so infinity is not a real number. So, that is why it does not belong to this one. So, that is why we always take r minus 0 in that. So, A is equal to 1 by x. So, from here I can say that 1 by x into x, that is going to be 1 for all x belongs to the set of real numbers, and this inverse is unique. And from here I can say that A is equal to 1 by x is the, so it is the multiplicative inverse of x, and also it is unique. And then we define the next one is fourth one. Now, we take that if I take any two x and y belongs to this one, then because I am going to show that it is a commutative. So, we multiply any two real number, that is also always this is true for all x and y belongs to R. So, from here I can say that this is commutative. So, from here we can say that this is true, that it is commutative under addition, and this is also commutative under multiplication. So, from here now, after satisfying this one, the next one is that third property I have to define. Now, I know that if I take 1.5 multiplied by 3 plus 2, so this can be written as 1.5 into 3 plus 1.5 into 2. So, from here I can say that x dot y plus z, I know that this can be written as x y plus x z, because that is true for set of real numbers, and this is true for all x y z belongs to set of real numbers. Or I can write x plus y dot z, and this is also equal to xz plus yz with the multiplication sign, and this is also true for all x, y, z belongs to R. So, from here I can say that the dot is distributive or addition. So, from here I can say that the set of real numbers under addition and multiplication is a field. So, it is a field, and whatever the field R is a field, so obviously it is a group all in that case also under the operation addition and the multiplication that we have already discussed. So, from here we can say that set of real number is also a field. The same thing, because I know that R, the set of rationals, is a subset of reals. So, in this case I can show that this Q is set of rationals is also a field, that we can satisfy all the properties. And then from here, because when I know that sum of two rational number is a rational number and product of two rational number is also a rational number. So, we can show that set of rational number is again a field. So, now after defining the groups and fields, now let us start with the terms what is called the vectors, because generally we know that the vectors are represented by a sign like this one. So, this is a vector which has direction as well as magnitude. And I know that the direction, so if I have this vector, then the direction is represented by this sign. So, this is divided by its magnitude. So, in that case it becomes the directions. So, these vectors we know that these are called vectors. So, it is a x vector and I multiply by some scalar a, then it becomes ax, where in this case my a is positive. If a is negative, its direction will change and then it will go in this side. If it is my ax when a is negative, and if a is 0, I will get this point. Now, these vectors we already know, but in the vector spaces we can define different type of vectors. And what is these vectors? So, now a polynomial Px, like I represent by a0 plus a1x plus a2x square up to a n x n. So, this is a nth degree polynomial is also a vector. Or I take a matrix, suppose I take 1 0 1 1 2 3 1 minus 1 0. So, it is a matrix 3 cross 3 matrix. So, it is also a vector. Or I take a set of functions, like suppose I take f(x) is equal to sin x or exponential or any function log x. So, these are also a vectors. So, now a vector does not mean that whatever the vector we used to take in our schools, that is the only vector. Even a matrix or a function or a polynomial, it can be also a vector, and more many. So, from here we will take the different type of vectors to define our next definition, and that is called the vector spaces. So, this is the main content of this introduction to vectors algebra first. So, in this case we define what is called the vector spaces. So, as the name suggests that suppose we have some space and that space is made up of different type of vectors. So, this is my vectors belongs to that space. Space means in which some properties are defined, then only we can say that it is space, and then based on this one we call it a vector space. So, generally the space means where we can walk, we can move anywhere. So, in the general sense the space means that person is having the freedom to walk in any direction. So, that is called the space. So, from this way what is called the vector space. So, let us define the definition of this one. So, what is the definition? A non-empty set V defined on the field F. So, V is a set non-empty set over the field F. So, field is there. So, a non-empty set VF is called a real vector space. So, we start with the only real vector space first, or it is also called a real linear space if the following axioms are satisfied. So, real vector space means my F is set of real numbers. So, the field is a real numbers. So, we are defining the V over the real numbers. So, that and it is called the real vector space. So, now we have to satisfy the following axioms, only then we will say that it is a vector space. It is made up of vector and it is a vector space. So, first one is that the first part is that there is a binary operation addition defined on V called addition or vector addition, or I also call it vector addition. There is a scalar multiplication defined on V. So, scalar multiplication, the elements, because in this space we have vectors. So, where is the scalar multiplication? The scalars are coming from here. So, I can say that scalars belong to field F. So, whatever the field we are taking, so scalars are coming from that field and vector is already there. So, scalar multiplication means I multiply a scalar, suppose we call it alpha is a scalar and multiply to V. So, that is called the scalar multiplication of a scalar with a vector. So, that is called the scalar multiplication. Now, after defining these two, addition and scalar multiplication satisfy the following condition. So, first we have defined the binary operation and then we satisfy this condition. So, the first one is that V is a commutative group for addition or under addition. So, it should be a commutative group under addition. First thing is that. The second thing is that alpha is a scalar. So, we generally take alpha, beta, gamma like a scalar and u, v, w with the for the vectors. So, a alpha scalar multiplication u plus v, it should be alpha u plus alpha v for the scalar alpha, and these are the vectors belong to this one. So, I can say that the scalar multiplication is distributive over the vector addition. So, this should be satisfied. Now, from here alpha plus beta, now I am taking the addition of the scalars u. So, that should be equal to alpha u plus beta u for scalar alpha, beta and u. These are the scalars and this is the vector from taken from the V. So, here we are adding the two vectors and then multiply the scalar. Here we are adding two scalars and then I multiply the u. So, this way we have the distribution of alpha plus beta over u. So, vector space is then the next one is that if I take the alpha into beta u. So, just I multiply alpha beta u, then it does not matter I multiply by alpha beta with the u, or I just change the position beta here and alpha u. So, these conditions are satisfied for any type of scalars alpha and beta and for the vector v. And the last property is that 1 into u should be u for all value of u, where 1. So, 1 is that is an multiplicative identity. So, 1 is not the 1 we have a natural number 1, it is a multiplicative identity and we generally represent the multiplicative identity with 1. So, that should be satisfied. So, this is the remark, a complex vector space is defined analogous by using complex numbers instead of real numbers. So, the same way we can define the set of complex numbers, and then if we satisfy the given condition of the vector space, then it is become the complex vector space. And also this is the remark, the real or the complex numbers used for the scalar multiplication in the definition of the vector space are called scalars. So, as I told you that the scalars are coming from the field. So, if that field is a set of real number, then it is a real vector space. If it is a complex number, then it is called the complex vector space. So, for example, that it is a very important vector space we are going to define. So, let Vn be the set of all ordered n tuples of real numbers. I am defining with the real numbers now. An element of Vn can be written as with this n tuple where xi are reals. So, for example, if I take V2, so V2 I am just defining the set of x1 and x2. So, this is the 2 tuple I am taking and where x1 and x2 belongs to a real number. So, this is basically if you see, then this is R cross R. So, xy plane, the whole plane we are defining. So, that is my V2. Similarly, V3 is the 3D, V3 is a set of all where x1, x2, x3 belongs to R. Okay. So, this is equal to R3, this is equal to R square. So, the whole space we are defining. So, V1, V2, V3 that is okay. V1 is just the I am defining, for example, I am defining with the real line. So, this is V1, this is V2, V3, and then the same way we can define the Vn that has n tuples there. Now, it is first thing is that we want to check whether it is a vector space or not. So, we can show here that Vn is a vector space under usual vector addition and scalar multiplication. So, it is a vector space under usual vector addition and scalar multiplication. Usual means the usual way we take the addition of the two vectors, because I know that this is the vector basically. it is a vector. So, how we can define? So, if we can show it by showing the properties that, so now we can check that first property is that Vn is a commutative group under addition. So, this is a commutative group because we know that if I take a element, so let us take the element, suppose I take x and y belongs to Vn, then suppose I take x is equal to, it is x1, x2, x3 up to xn, and y is y1, y2, y3 up to yn. So, these are the element belongs to Vn. Then we can show that x plus y will be x1 plus y1, x2 plus y2, and from here I can define xn plus yn. So, this is the way we generally add two vectors. So, that is why it is called the usual vector addition. It is a component wise addition. So, this also belongs to Vn. So, it is closed under addition, and then we can define that it also satisfies the other property. So, that we are going to discuss in the next lecture. So, we will stop here. So, today we have continued with the definition of algebraic structure, that field, and then after the field we have defined that how a vector space can be defined for different type of vectors, and then in the next lecture we are going to continue with this one. Thanks for watching. Thanks very much.